Welcome to Semantic Web Technologies, Lecture 1, the Web of Data, Part 7, Applications in the Web of Data. In the last parts of that first lecture, we have seen that there are lots of problems that are connected to the lack of explicitly given semantics and meaning of information in the web. And we have got a first clue about what is possible with the help of the semantic web when this previously only implicitly given information about the meaning is made explicit. And then, of course, it's accessible by machines and can be interpreted correctly, with the goal that it will also be possible to deduce new knowledge from existing knowledge. So let's take a look at a few applications that are already existing in the semantic web and the web of data. The web of data as today is most likely represented by the so-called linked open data cloud that you can see here. So this is a huge cloud of documents and information that are provided with the help of RDF, the Resource Description Framework. So there are billions of facts, actually 31 billion facts and more by 2011, with more than 500 million links among each other of facts that are grounded in knowledge bases and that are publicly available on the web, and they describe many different areas of information and of our daily life. For example, there are ontologies and facts in the linked data cloud about general information, about encyclopedic information like in the Wikipedia. And there is, of course, also many information related to science and bibliographies. There is many information related to multimedia on the web, or also many information related to medical and biological science, because this is an area where, for example, in artificial intelligence and natural language processing, for many years there has been made big progress. So this can be considered as a huge global database where, for example, it's applications like the BBC program web page, music program web page, is referring to. So this is a web page of a new generation. Also, it looks like a traditional existing web page. But what is different about this web page? It's the program of the BBC Music, for example. For every artist that you see here, information can be displayed on the web page about this artist. And this information really, it's recent information and is provided, for example, by DBpedia, which stems from Wikipedia, and, for example, MusicBrainz and Discogs, where there is bibliographical information about the latest published records and albums of that musicians or of that artist, and also tour information and stuff like that, what can be interesting. But the interesting thing about that is that there is no human journalist or a web page designer who does this or provides this information in a manual way. So this information is collected automatically. So this is really special about this information website. So the information is dynamically aggregated from external, publicly available data. And this data is not simply captured by methods of screen scraping. It means they don't look at the HTML page and try to get out the information with the help of statistic and natural language processing methods. And there's also no specialized API programming interface to each website where they are collecting data. It's only a single, based on web technology, a single standardized API that can be used in the semantic web and is based on simple HTTP. So also firewalls and stuff like that, they might not be considered or must not be considered. The data that is used is available as linked open data. It means the data about the artists and about the works of the artists, they are provided in DBpedia or MusicBrainz and Discogs in the form of linked data. And it can be accessed via a simple HTTP request. So a simple request from the web browser usually also can be used to access this data. You do not need a special API. And the data is always up to date without manual interaction, because when the original data changes, the web page is a dynamic web page that is created on runtime with help of the live data from all these sources, will always be up to date. So this is, of course, a nice thing. So this is one thing that already exists. But now let's take a step further. What could it mean in the future? For example, for search engines, when semantic data is explicitly given on the web. So for example, if we ask a search engine in document retrieval with a search term and the query string Jaguar of 2000, then of course the search engine has to distinguish, do we mean Jaguar the cat? Do we mean Jaguar the car? Or, when we are computer scientists, or if we are computer scientists, do we mean Jaguar the operating system? So what has to be done, for example? We have to refine this query, and the search engine might ask, pardon me, which of the three do you mean? And we can refine it and can say, oh, we mean the car. Then, of course, the search engine has to interpret the rest of the phrase, the 2000, for example. And this is also ambiguous because it can mean several different things. It can mean, of course, the construction year. I have to go back one. It can mean the construction year, or it can also mean, let's say, the power of the engine of the car. But 2000 is most unlikely to be 2000 horsepower. Okay, but what you have for the car is you have some kind of knowledge representation where you can look up what is the most probable interpretation of 2000, and you can answer according to that. But of course, there are several different problems related to that. And one general problem is, okay, how do I interpret correctly the query string? I have to take somehow into account the context of the user, the context the user is working in. What has he asked just before, or what is his usual preference? Does he mean cars? Does he mean cats or something like that? And of course, then all the entities that are connected to the terms in the natural language query string, they have to be correctly identified. So this mapping between terms and identities is also difficult and mostly error prone. So what you need is some kind of automatic disambiguation. And all this process has to be done in an automated way so that the user, for example, doesn't notice it. Or on the other hand, the user has to be asked, just for example, pardon me, what do you mean exactly? Do you mean this or do you mean that? And then you run into problems because of the usability of that process. If you are asked 1,000 questions, then nobody will use this search engine because it will take much too long to get to the right answer. And of course, your personal context has to be taken into consideration. But we can go one step further. So, for example, if I'm driving my car and I see that I need gas, then I ask the question, where can I fill up the tank at a considerable discount, for example? And then I will get the address. I will get, for example, where gas is the cheapest. And of course, my navigation system that has to follow the most fuel-efficient route to that fuel station. And maybe also I have to drive in a way that the fuel really is sufficient to reach that gas station. So I have to drive at half throttle for saving fuel. And this also can be managed in an automated way from some kind of a fact retrieval search engine. So when I ask questions in natural language and I want an answer in natural language and not a bunch of web pages, which is document retrieval, then we are talking about fact retrieval. And if you want to try this out, you can try, for example, Wolfram Alpha, which is an already existing fact retrieval search engine with a huge knowledge base behind it. And there it's possible to give your question in natural language and then, of course, to find the answer. Another thing that you are not accustomed to when searching in the web today is the so-called exploratory search. So, for example, maybe you start your search with Neil Armstrong He was the first man on the moon. When the search engine has a knowledge base in the background, it made it use that Neil Armstrong was on a mission called Apollo 11. And there are other members of that mission. For example, you will find his fellow astronauts, Michael Collins and Buzz Aldrin. And furthermore, you might have the information that Apollo 11 was part of the Apollo program. And there were other missions, for example, Apollo 13. And maybe you know it that with Apollo 13, there was a near accident in space. So Apollo 13 also belongs to a class space accidents and incidents. And from the class space accidents and incidents, you will possibly also find or get connected to the Space Shuttle Challenger incident. So you will get connections in that knowledge base and you will find new knowledge, what is possibly interesting for you and that you didn't count to find in the first place. So this is some kind of, it's called serendipity, to find something, to make a happy finding that you wasn't aware of that it really existed beforehand. So this is possible, this kind of exploratory search, when you have actual semantic information in the background. If we look at the web today, then we have to consider we have web documents. And on the one hand, we can look up the web documents with the help of our browser, which is a representation service. But we use another service to find these web pages, these web documents, with the help of retrieval services, for example, with Google. In the semantic web, this is handled somehow different, in a different way. There you have the user, and on your desktop or on your mobile phone, you will have some kind of a personal assistant. And this personal assistant will make use of intelligent infrastructure services. And these services are accessing the web documents, and they are collecting the information that is relevant for you. And the personal assistant will decide how to connect the information and how to present this information to the user. So we can distinguish 3 different generations of web documents. In the first phase of the web, we only had so-called static web pages, and these static web pages were programmed or represented as HTML, and the format was represented as a style sheet with CSS. Then there came the second generation, which were dynamic web pages and interactive web pages. It means that on the one hand, we could interact. We didn't have static web pages. We had interactive elements that were programmed with the help of JavaScript or also by applets. And on the other hand, we had content management systems, and there were templates, and these templates were accessing database information, and the web page itself that was represented in the browser for the user built up or was created in a dynamic way from the template and from the database content. In the semantic web, we will have the third generation of web pages, and there we don't have existing web pages. We have something like virtual web pages. It means we have our information assistants, and below there are these infrastructure services, maybe in the form of a netbot, and they are collecting the information that we need from the data sources we are interested in and create, according to our preferences, an own virtual web page. And our preferences, of course, are taken into account. So my desktop management, my personal information management learns, with the help of machine learning, how I like to have my information presented. So a user model will be created automatically, and the layout of the web page will be adapted according to my preferences and to my likes. And this, of course, will develop over the time together with me as a user. So these are the 3 generations of web pages. And if we look at computer science in general, the toolbox that we have for the semantic web, of course, are a bunch of standardized languages. and knowledge representations that we have learned or that we have seen first in this semantic web technology stack, for example, XML, RDF, OWL, or also rules, given it's RIF, it's the rule interchange format. And we have tools to use this information in the web, so there are also techniques how to get these representation languages of the semantic web into the web. This is done, for example, with RDFA and Gradle. We will come back to that later. And in general, several fields of computer science are addressed by the problems that arise in the semantic web. First of all, of course, it's artificial intelligence, and there it's logic, because we need logic for a formal knowledge representation. Of course, we need linguistics. We want to understand what, for example, a query string means. We want to map language entities to semantic entities. Then, of course, there are access restrictions, cryptography, and stuff like that. We have to take a look at data bias technology, because the knowledge representation, they have to be stored in a persistent way. And their traditional databases, for example, relational databases, are not very well suited for that task. We will see that. Then, of course, we need theoretical computer science, because we have to trim, we have to tune these algorithms to make them as streamlined as possible, and we have to take into consideration the complexity of all that we are doing here. So it means the runtime complexity or also the storage complexity. Then, of course, computer architecture is involved, software engineering is involved, systems theory is involved, and also in the end, computer networks. So it's lots of stuff that we are talking about or will be talking about in the next 5 lectures. And in the next lecture, we will have a closer look at the basic architecture of the semantic web. And you will get the answer to the question why this is not an apple.